Welcome to my lecture course, that is aspects of biochemical engineering. In the last lecture, you may remember that I tried to discuss how to analyze the different type of reactions. So, we have a basic formulation that we shall have to remember before we analyze any kind of reactor, that rate of input plus rate of that rate of input plus rate of generation equal to rate of output plus rate of disappearance plus rate of accumulation. Now, what I told you that in case of this steady state conditions, the rate of accumulation should be equal to 0. Now, what do you mean by steady state condition? When the concentration in different portion of the reactor remain unchanged with respect to time. So, that is the steady state, that is only possible when a rate of accumulation is 0. So, this is the equation. So, our equation is the rate of input plus rate of generation equal to rate of output plus rate of disappearance plus rate of accumulation. So, this is the basic equation we have. Now, when we analyze the reactor, I told you we shall have to consider only one parameter. As for example, suppose we are using any kind of microbial system. So, we have three different things simultaneously take place. One is substrate degradation, another is cell mass formation, and there is your product formation. So, we can do the analysis with respect to anything with respect to substrate. So, when we do the substrate balance, then will be rate of substrate input plus rate of substrate generation equal to rate of substrate output plus rate of substrate disappearance plus rate of accumulation. Same thing happen to products, same thing happen to your cell mass. And but if we can do the analysis with respect to energy also, rate of energy input plus rate of energy generation equal to rate of energy output plus rate of energy disappearance plus rate of accumulation of the energy. So, this is the basic idea, that basic equation that we use for the analysis of the reactor. And I told you that whatever reactor we have, broadly it can be divided into two types. One is batch, another is continuous. We use the fed batch reactor while we have the substrate inhibition problem. Now, in the batch reactor, that we take the, as I told you, you take the substrate at a time, allow it to react. After the reaction is over, you take it out. In between, you are not putting anything to inside the reactor, and you are not taking anything out of the reactor. But in the continuous system, I told you that initially, particularly if you look at CSTR, first we operate in a batch mode, let the reaction take place. When the rate of reaction is maximum, then we start feeding one end and take the product from other end. So, for whatever flow rate we have inlet, that same flow rate will maintain in the outlet, so that volume of the reactor remain constant. Now, today I want to discuss some kind of numerical problems, so that your conception of the process will be very clear. Because what we are interested to know a couple of things. We are interested to know what is the percentage conversion take place during this process. Also, we want to know what is the volume of the particular reactor for whenever you go for batch process, whenever you go for continuous process. Now, before I go to the PPT slides, that let me show you something, so that it can help you for understanding the process. Now, I told you, when you talk about the batch process, the T batch, I told you this is equal to what? This is equal to minus dCA. Suppose the reaction is A to B divided by minus RA. So, this is like this. Now, this is Ca0 and this is Ca. Now, I told you C A equal to C A 0 into 1 minus x A. X A is the fraction of x that is converted. So, I can write C A d C A equal to C A 0. C A 0 is a constant. I can write this is equal to x. So, this same equation we can write in the dxa form like this, dxa by minus R A, and there 0 to x A. This is what we do. Now, when you suppose when you talk about the design of the reactor, first we shall have to have the basis. And what is the basis? Suppose we want a certain amount of product formation. Let us assume we want to produce 100 kg of product. Once we want to know the 100 kg of product formation, first we shall have to find out from the stoichiometry for producing 100% 100 kg of product, what is the substrate required. So, there will be some kind of stoichiometry between the substrate and the product formation. So, with respect to the stoichiometry, we can find out amount of substrate required. Now, this might be, this is with respect to day, am I right? So, per day you want to produce, so this also you can say per day how much substrate is required. Now, from the stoichiometry we find out the theoretical amount of substrate required, but in practice you might be requiring little bit more. So, you have to divide by the conversion efficiency, percentage conversion efficiency. So, suppose percentage conversion efficiency is 95%. So, we divide by 0.95. So, this is how we can but question come how you find the volume of the batch reactor. So, what we shall have to do, we know that the main bottleneck of the batch process is the downtime, because suppose this is a batch and after the operation is over, you have to take the product out, again clean the vessel, and then you have to refill the vessel. So, that requires some time. So, T total equal to T batch plus T downtime. So, that so if we know, so what I want to tell you that when you find out the volume of the batch reactor, we shall have to first calculate how much batch we can operate per day, the number of batch per day. Then from that we shall have to find out that how much substrate, then we shall have to find out how much substrate is required. Substrate is required per batch, and then we can find out the volume of the reactor. So, when you want to find out T total, what you have to first you have to calculate T batch, and I showed you the T batch is what? T batch equal to minus dCA by minus RA. So, from that CA 0 to CA you can easily find out that that what is this batch time required, and you assume some time and then you find T totals. Now, number of batch, how you can calculate? This is equal to, suppose per day you have given 24 hours. So, number of batch is the T total. Suppose this is T, and in the basis we have taken the 100 kg of product per day. From that you can find out how much substrate is required per day, and from that since we have two batches, so amount of product per batch will be what? Per batch equal to 50 kg. Am I right? 100 kg divided by 2, number of batch is 2 if we assume this per batch. So, from that you can find out how much substrate is required, and if you know the substrate required, then you divide by initial substrate concentration, you will get the volume. So, this is how you can find out the volume of the batch process. Now, if you look at the volume of the continuous process like tau CSTR is equal to what? Is equal to CA0 minus CA by minus RA. So, RA you can easily find out from rate of reaction, you know, from the percentage conversion you can find out what is the CA0 and CA value, from that you can find out. This is equal to what? V by F. So, F you can find out from the amount of, suppose we want to produce 100 kg of product per day. So, from that you can find out how much kg of substrate you require per day. So, if you know initial substrate concentration is 0, so you can find out this is flow rate volume per unit per time. So, you can put this value, you can put this tau CSTR, calculate tau CSTR value, you can find out the volume of the. Same thing happens, same thing applicable for tau plug flow reactor. Tau plug flow reactor is what? This is same as batch process divided as dCA by minus RA. So, if you know this and same correlation is hold good, you find out the F in the same way you can find out the volume of the reactor. So, now, let me take the first problem. The first problem deals with a homogeneous liquid phase reaction A to B, and this is a second order reaction, minus R A equal to K into C to the power 2. Take place with a 50% conversion in a CSTR. What will be the conversion if the reactor is replaced by 6 times as larger, all else remains unchanged? And what is the second part? Second part is that what will be the conversion if the original reactor is replaced by the plug flow reactor and all else remains constant. So, you have two different approaches. Is the one first case, what we want to do, we want to increase the volume of the reactor of the CSTR 6 times, and second case we want to replace the CSTR by plug flow reactor. Two different approach, we want to find out how the conversion efficiency changes. Let us work on that. So, first we have in this problem, if you look at it is given here, what is given? 50% conversion of substrate, am I right? A 50% conversion of substrate means X A is 0.5, X A is 0.5. What is X A? X A I told you previously several times is this CA0 minus CA by CA0. This is X A. So, what is the equation that we have? Tau CSTR equal to, I told you, tau CSTR equal to CA0 minus CA by RA. Now, this is equal to CA0 into XA by RA. So, this is how it has come, and then this is the rate of reaction, that K into CA squared, and this is this should be equal to V by F, what I told you previously. Now, then we can analyze the reactor like this: CA0 into X and the K into CA0 1 minus X, where that that whole square, we can find out this is equal to this, and finally we can come this expression, because CA0 1 CA0 will cancel. So, 1 CA0 will remain here. Now, put the value here, you can 0.5 and 0.5 per 50% conversion. Then we have here we have this equation, we have 2 by K CA0 V by the. Now in this problem, what first part, we want to increase the volume of the reactor 6 times, am I right? So, your now new volume will be 6 into V CSTR. V CSTR was the previous volume, is 6 times we want to increase. Let us assume the conversion efficiency at that time is XA, and this is like this. This is the equation, same equation what we have written previously, that we can write here. Then this equation we can write the expression like this. This is equal to 6 because V CSTR by this this is we have already written this is equal to this 6 into 2 by k. I can show you this is what we have written now. So this is what. So this is we have calculated previously. This is the new approaches that we have. This is equal to this. Now this equal to what? This equal to 2 by k Ca0. So this we can do it here. So this is how it has come. This is come. So we can solve this quadratic equation. We find two values. One is 0.75 and 1.33. Now more than conversion efficiency, more than 100% is not possible. So we take 75%. So XA is the 75% when we replace by the. So previously the conversion was 50%, and when we increase the volume of 6 times, then conversion will be 75%. So this is how we can solve this equation. Next part is very interesting, that if what I am saying that if a CSTR is replaced by the plug flow reactor. Now what is the expression for plug flow reactor is this one. So we can solve this equation like this, because we know this is k into Ca0 square 1 minus Xa whole square. So this will come here, and then we can, this is equal to this V by F, and this is equal to that in case of CSTR it is like this. We told that everything is remain constant. So we can equal to like this. If everything is constant, how it what will be the conversion in the plug flow reactor. Now if we equilibrate this, then we find this 2 by k into Ca0, 1 by k into Ca0 Xa 1 minus x equal to, then we can solve this equation. This will cancel, this will cancel, then only one equation, one unknown, we can easily solve the Xa value. So we find the 67% will be the conversion if we CSTR replaced by the plug flow reactor. So initially that in case of CSTR is 50% conversion. Now if you replace the same thing by the plug flow reactor, it is increased to 67%. So you give some kind of impression that what happens if the CSTR is replaced by the 6 times CSTR, the volume of the reactor is replaced by increased by 6 times. What will, how the conversion efficiency changes, and second case we try to find out if the CSTR is replaced by the plug flow reactor, how the conversion efficiency changes. Now next problem also very important. Let us walk with the next problem. This is like this. This is, you see, the aqueous feed A and B. This is feed flow rate is given 400 liter per minute, and what is the A concentration? 100 millimoles A per liter, and what is the B concentration? 200 millimoles B per liter, and to be converted in the CSTR. So here I want to tell you one thing, that when your reaction is A plus B equal to R, that means that indicate 1 mole of A react with 1 mole of B to give the 1 mole of R. So this is the stoichiometry is like this. So here in this particular case, so your concentration of A is less as compared to concentration of B. So limiting factor is the A, that we should remember. So the kinetics of the represented by this equation. So find the volume needed for 99.9% conversion of A. Since this is the limiting factor, so this problem is to convert 99.9% of A, what should be the volume of the previous problem was that what is the percentage conversion efficiency. Now, in this problem we have given that if we know the percentage conversion efficiency, what will be the volume of reactor. Let us see how we can solve it. Now, first let us whenever we solve any kind of equation, I request all of you that please write down all the data, that whatever given data is given, you write down one after another. Here in this problem you see that flow rate is 400 liters per minute. This is the flow rate, volumetric flow rate. And what is the CA0 concentration? 100 millimoles of A. This I can easily convert it in moles of A per liter, because this is millimoles. If you divide by 1000, then it will be 0.1 moles of A per liter. Now, second case, that if you see Cb, similarly you can calculate and find out 0.2 moles of A per liter. So, we try to convert this millimoles to moles. Then XA, the conversion efficiency is 99.9%. So, XA value will be 0.999, and K value in this equation is already given, 200 moles per liter inverse and minute inverse. Now, if you put these values here, that here with this equation we have 200 in Ca minus this, and this is the conversion of A take place. So, this is to be deducted with Cb, because this is the equimolecular reaction, and then we can find out the tau CSTR. Tau CSTR is the space time of CSTR. I told you space time. Space time means that the time you are allowing a particular volume of the reactor, volume of the liquid resides in the reactor. So, what is the space time you are giving? This is equal to Ca0 into Xa, and this is the rate equation. I can put it here, and then we put the data, all the data you can find out tau CSTR. This is coming about 49.9 minutes. So, this is how you can calculate the time required for CSTR. Now, once you know that tau CSTR, now our equation, what is our equation? Equation is tau CSTR equal to V CSTR by F. So, now if we already know F is 400 liter per minute, and time we have. Now, sometimes let me tell you, sometimes when you give this unit, you should be very careful what is the flow rate of this unit. Sometimes if it is in per day or per hour, and your tau CSTR is in minutes, so you have to convert into the per minutes, and then you multiply this, you will get the volume of the reactor. Now, repeat the problem, but for a CSTR. So, let us see that this is the conversion, that this is with respect to CSTR. Now, we want to show the similar type of things that we have when we can go for plug flow reactor. But previously we are talking about the CSTR. Now, in the plug flow reactor, your rate constant will be the same, the rate of reaction is same, that we can express like this. Only your expression is like this. I told you this is tau plug flow reactor is equal to minus dCA by minus RA. Okay. So, this RA is same, the dCA I told you what is the CA. CA equal to CA0 into 1 minus XA. Now, if you do dCA is equal to what? Minus CA0 into dXA. This is exactly, so here there is a minus sign, so this will be removed, this will be plus, minus minus will be plus, this is minus R, and minus R value I can take it from here and put it in this equation like this. So, next we can find out here that tau plug flow reactor equal to Ca integration 0 to x a equal to d x a, and this is the equation that we can write. Only we can take the common of Ca 0, so that this ratio will come Cb 0 by Ca 0, and this, and this ratio at the initial stage is 2. We know that one is 200 millimoles, another is 100 millimoles, and Xa is the percentage that fraction converted. Then this equation, if we solve it, it will come in this form. So it is, you can see it, this is if you have, then if you do the percent differentiation of this, you will get this particular expression. This is 1 by k Ca 0 ln to Xa by 2 into 1 minus Xa. Then if we put that then values here. Now, if you look at previous equation that we have tau CST, the k into k value is known and Ca 0 is known. So, this value, if you put all these values we put here, then we will get the tau plug flow reactor. The tau plug flow reactor we can easily calculate. This is coming about 0.3 to 31 minutes. So, I can just show you previously that when in case of CSTR we calculated it is coming quite high, 49.9. Now, it is coming quite less actually. So, volume also is coming quite less. This when you calculate this with the flow rate is basically same in the continuous system, then we can find. So, we find that volume of the plug flow reactor is much less as compared to that of the CSTR. So, in this particular presentation, what I try to point out, two important aspects that how to analyze the batch as well as the continuous reactor, and how to calculate the conversion efficiency of the continuous process. Only one thing I can highlight that in case of CSTR, there is we have continuous start tank reactor. So, it is the main purpose of the agitation to make the homogeneity in the reaction mixture, but in the plug flow reactor the liquid flow from one into others, and when it flow one fund there is no axial mixing, there might be radial mixing. So, that is the, if you have that pattern, your expression is changed, and with that we find out that percentage conversion for the same type of reaction is different when you go for CSTR as well as plug flow reactor. And only the batch reactor problem I didn't solve in this particular lecture, that I am going to solve in the coming lectures, that I just show you how you can find out the volume of the reactor. Now, volume of the, when you calculate the volume of the reactor, I want to emphasize that first you have to find out that how much product is to be produced per batch, and how we can find out, because you have from the first we shall have to calculate what is the total time required for the batch process. Now, total time of a batch process is nothing but batch time plus your downtime. Downtime is nothing but idle time, and this comprises of time required to take out the liquid from the reactor and cleaning the vessels, refilling the vessels, because this is called downtime, and other way we can call it also idle time. Why idle time? Because during this time we assume no reaction take place. So, so this time is to be added with the total time, and when you get the total time, so if we suppose we have a basis that we want to produce 100 kg of product per day. So, one day comprises of 24 hours. Now, if your total time is 12 hours, the number of batch per day will be 24/12, that is 2 batches. So per batch you have to produce 100/2, that is 50 kg of product per day. So if you know that how much product you have to produce per batch, then from that you can find out how much substrate is required per batch. How you can find out? You can find out from the stoichiometry of the reaction. Also, the stoichiometry of the reaction will give you the theoretical requirement, but in practice the 100% conversion is not taking place. So we can assume some conversion efficiency of the process, and from that we can find out that what is the exact amount of substrate required per day. Now when you find out that exact amount of substrate required per day, then if you divide by initial substrate concentration, then you will get the volume of the reactor. Thank you very much.